Hello, welcome to Supercognition. So Aubrey and I are just having a conversation about intuitions and parallels between biological thought, rationality, and what we have been playing with deep nets and these concepts, and looking at the overlaps and the intersections between these. So we're just kind of having a general discussion today and opening that up to you guys on this channel. So we're not reviewing a paper today, just exploring a few ideas. So Aubrey, go ahead.
Absolutely, and thanks for the intro, Zach. We've been having some really interesting conversations on rationality versus intuition, trying to understand the human mind from the inside out. I'm a big fan of introspective meditation style practices that allow us to explore the structure of our own thoughts. And I'm becoming increasingly fascinated in how the way those thoughts feel to me is expressing a great degree of overlap with what machine learning science is beginning to explore. So, one really dramatic example of this would be the idea of intuition and heuristics, the ability to catch a ball by reflex or to jump straight to the right conclusion as a domain specific expert solving a particularly wicked hard problem, as we have so many examples of great scientists throughout history doing. And what Zach and I have been exploring is this idea that we are neural nets by definition. Our brains are networks of neurons. And we spend our lifetimes training these nets, again, by definition, in order to optimize solutions for the problems that our lives tend to incorporate. Whatever we practice, we improve at, and that is perfectly analogous to the way machine learning algorithms are beginning to use deep learning techniques to optimize for particular problem domains. There is, of course, a lot more involved in what's going on between humans' ears, but machines are beginning to close that gap. And one of the big remaining pieces, which computer scientists, mathematicians, increasingly physicists, and of course philosophers have begun to explore, is the difference between structured, logical, rational thought and the intuitive, deep learned neural network type systems that appear to both be running simultaneously inside of the human brain. When we
Yeah.
look at the, I'll let you take it from here, Zach. I'm sure you have some interesting thoughts to share.
This is the classic distinction between the symbolic approach to AI, which, good old-fashioned AI or GoFi, and the more learned distribution, stacked composable functions with gradient descent. I think this is the classic difference here between something that has intuitions, but intuitions can be often wrong, something that's more perceptual, right? And if you look at what's solved in AI, it is the perceptual aspects of AI and not the common sense aspects of AI. So it's what is solved has been the parts of intelligence that are perceptual, that are intuitive, that are based on more statistical inferences and probabilities, and that is exactly, I think, what a deep net is doing, especially when you're looking at some of these larger models with attention mechanisms. It really seems like they are at human level for these perceptual type tasks, whether that's, I mean, they've exceeded the human baselines in almost every category of perceptual related activity, but they still lack in the common sense, right? The reasoning aspect. And so I think the key is to understand what is the combination between these deep nets and something that's more analogous to program synthesis or some kind of a collection of programs. And I guess some of the intuitions we've been playing with are what are heuristics, for example, and are the types of heuristics that humans develop fundamentally different from the, for example, than the biases that machines learn, right? And are the constraints on human heuristics, primarily energy based, so that they are very simple compared to the biases that we observe in neural networks, which are probably over parameterized because the whole network is allowed to learn, unless you have a more compartmentalized model that I think is going to be necessary to overcome catastrophic forgetting. And so, I guess the question is, how do we synthesize these two different types of, like, good old-fashioned AI, which is the symbolic mechanisms, right? And how much of that is useful or needed? Because we see a lot of effort now to try to do everything symbolic on a deep net, and it's probably, that's exactly what our mind is doing. So in a sense, we are doing this program synthesis, this symbolic manipulation. We're doing that with neural networks today, right? But potentially there's a more creative synthesis that we can engineer, where we don't have to run all of these, and where we're able to bring in more efficient algorithms for things like, I think that's one of the big areas of improvement with synthetic cognition, is that we actually get to insert optimal algorithms where running them on a neural network isn't optimal. And I think that's the whole point of the no free lunch theorem, right? Is that there isn't a single general algorithm that is optimal for every problem. And yet what we're doing with the human mind is exactly that. We want discrete memory. Okay, we do it on a neural network.
It's so much more useful to think about an ensemble of intelligences, which are each highly domain specialized and appropriate in a particular realm, as opposed to generalized intelligence as such.
Yeah, and I think we have, and that gets to the collection of heuristics that we apply. And we almost do program synthesis with heuristics when we're reasoning. We're taking a lot of underparameterized, overgeneralized. So anytime you have an underparameterized model, right, it's going to be overgeneralized, and but it's more energy efficient. And I think the human mind has had a fitness function which is largely based on the energy cost of computation, and that is largely absent in today's machine neural networks, right? And so there's no, in many cases, we don't reward the neural network in terms of its loss function based on how few parameters it uses, and that needs to become a central tenet, a central fundamental principle in all of our architectural designs, right? Because if we can take the same, for example, so if we can take a neural network and using 1 million parameters, predict something that could be done with just a few parameters, that's very wasteful. And so something that we've been excited by is something Max is working on, trying to learn the shortest programs with mathematical functions that can approximate a given, right? So I think you want to jump in and talk about that?
Yeah, absolutely. That would be Max Tegmark with MIT. In particular, this paper would be AI Feynman, a physics-inspired method for symbolic regression, and we're planning to explore this in much greater depth on a future episode, potentially even have Max on the show, which would be awesome. But what's really inspiring here for me is this idea that intelligence may well be computational substrate independent, which means that if, to put this humorously, if the toaster oven has enough neurons in its brain, it's probably capable of the exact kinds of thought that I am. However, there's more to it than that. Intelligence is also almost equally certainly evolutionary constraint derived. Human intelligence is a function of optimizing for the fitness function of survival itself, which may be one of the reasons it's occurring to me that efficiency plays such a critical role in the way that we humans think. It's almost amusing how much more both amicable and rational we are when we're well fed, for example. I think we can all relate to the experience of having low blood sugar, skipped a meal or two, and suddenly I'm cranky, very linear, and less creative and divergent in my thought. And there's clearly survival utility value in that adaptive behavior of the human mind in order to go out, find food, satiate basic survival needs, and then switch back into higher level thinking mind mode again. It's really interesting to explore constraints. It's really essentially this whole principle that necessity may indeed be the mother of invention. And the more constraints and ecological niches and other adaptive environmental dynamics of a system, the more opportunities there are for developing intelligences to diverge in potentially interesting sorts of ways.
Yeah, and I think one of the key ways that you can articulate this fundamental constraint of efficiency would be to say that the loss function of a neural network needs to not only quantify the absolute distance error or the squared error of the predicted outputs, like it needs to divide that over the complexity of the model that was used in order to create that prediction, right? So the real value of intelligence is the density of that intelligence to computational cost. In other words, it's the prediction value over the energy cost and loss and whatever other constraints you're trying to optimize for. But traditionally, in most of the deep nets that we're using today, we don't incorporate parsimony into the loss function. So we're not actually looking for these parameter stingy models as much as we should. And I think we need to have architectures that really reward the most parsimonious models, and also bring in more primitives, in other words, more mathematical primitives for simple functions that can be composed. And I think that's what Max is trying to do with his AI Feynman approach, is actually look for something that would automatically discover, for example, the laws of three bodies, the laws of gravity, or the laws of anything that we have through brute force and through the intuitions of scientists. Anything that we have basically discovered in the universe is compressible down to a simple equation. Even things like the Feynman diagrams, or the math behind the different quarks, or any of these equations that we have been able to compress, where we've been able to compress reality down to something incredibly simple and parsimonious, right? Some incredibly compressed equation. How do we go about creating something that searches over those spaces and discovers those? And then how do we incorporate that into deep learning? Because right now, what we have, like the state of the art in like language models, you have GPT-3, and it's an autoregressive model, right? So it has a context window. It's always has a few thousand tokens, for example, in its context window. It's trying to predict the next token given an input sequence, and that feels very much like what the human mind is doing when we're speaking. It seems like we're speaking in an autoregressive way. In other words, we're not rationally planning every next word, and we're just reading like ahead off of some autoregressive distribution in our mind, some idea that we can't that's latent, and we can just read it with this read head that's autoregressive. And we also have this critic in our head, which is some kind of a filter that kind of guides. It's almost like a tree search that guides that autoregressive head at every time step. It's looking at a couple, maybe just a few next possible tokens in that autoregression, and it's predicting or selecting, let's say, one of them based on some estimation of their value function.
I've actually personally experienced this exact scenario playing out inside my own head.
That's what it feels like.
Yes.
Yeah.
In my specific case, I went hyponatremic during an extreme athletics event which is potentially a life-threatening condition if it's not addressed. Thank for me it was. It just means you're basically drinking so much water that your blood electrolyte levels drop to the point where your brain and body are no longer functioning optimally. The recovery window for me over the next, I would say 36 to 48 hour period, I felt great, but I had little to no working memory. And this is apparently relatively common for people who experience this firsthand, but I felt like myself. I comported myself in my usual ways, and yet I had multiple conversations with both friends and strangers during that window in which they would interrupt me halfway through a conversation and said, Aubrey, you just repeated the exact same 10 plus words that you did 30 seconds ago. Are you feeling okay? I think we can relate to caring for the elderly experiencing Alzheimer's. There's this emergent behavior of minds using language to communicate where they have the visual representations of ideas, at least this is how it feels to me, and some sort of translation layer between the conceptual space into the symbolic space of the words themselves representing attributes of those ideas arranged according to grammatical rules. And then ultimately the actual, I think we could call it the autoregressive model that strings those words together, composes them into sentences and larger language constructs, and can ideally recreate the concept in another mind. But that if there's a breakdown in any one of those steps, it can be quite enlightening to both witness and experience that.
Yeah. So right now, we just don't see any of these. So we have these incredible autoregressive models, like these massively scaled up transformers, which is GPT-3, right? And I feel like the transformer architecture is brilliant for this autoregressive task. I feel like that attention mechanism really just works. There might be better ways to implement it that don't have the quadratic memory scaling complexity that allow us to expand that token window from a few thousand tokens to much larger. Humans probably have a context window that's quite nearly infinite, right? And so it appears to be. So I think the autoregression part is in many ways solved by the current architecture. We need to make it more multimodal. We need to be introducing not just text to these models, but also video and audio and other modalities of sensory information, perhaps even electromagnetic wavelengths that humans don't have sensory perceptual senses for. So potentially parts of the spectrum that we don't see or hear or perceive. I think that would be also useful to bring into these models so that they can have a much more complete
we're finally going to answer Nagel's hypothetical of what it feels like to be a bat.
Yeah.
We could train a language model with the same sensory inputs that a bat would have, a multimodal net, and then ask it how it feels. I love this idea.
Yeah. I mean, it might as well have radar, sonar. It might as well have access to, the smaller wavelengths as well. So, it might as well be able to perceive, microwaves, and it might as well have access to the large wavelengths like radio waves. Why constrain it in terms of what sensory inputs it can, what interesting types of intelligence would emerge? For example, if we could perceive at all wavelengths of electromagnetic fields, right? So that's just a fun thought experiment. It's just a way to explore a whole new set of possibilities for what types of intelligence would emerge. Now, of course, I think most intelligence is basically symbolically shared, though, through language with the society that has already learned a vast amount about this universe and how it works. And so, of course, language provides the most symbolically dense form of information. If you were to try to, for example, compress ideas to the maximum, right? Then that's where language as a set of a sequential serialized set of discrete symbols provides the best context for compression, because it provides you with this context where the next word, the next symbol, can basically shape the meaning of the symbols that precede or proceed the symbol that I just gave you. And so we have this very dynamic thing we call language, which allows us to encode distributed representations into strings of symbols and then communicate that through this video call right now in a way that the same representations in terms of activation patterns become active in your distributed representation, your neural network. And so that is the beauty of language, the fact that it's this mechanism for taking the scrutable parts of these distributed representations, serializing them, compressing them, transmitting them through this serialized form, right, and then uncompressing them on your end in the same or approximately the same latent activation pattern of these distributed representations. That's incredible. And so it's incredible to see where GPT-3 is going with that.
The more shared experience your mind has with my mind, the more compressible those language symbols, words,
right,
sentences, references to popular culture, etc., can be. In a highly technical world, jargon, specialized vocabularies begin to develop, and that's perfectly appropriate because it allows for the enhanced compression of highly technical subject matter. If we continue zooming conceptually out, moving from the micro to the macro, I've been trying to imagine how it could feel for a language model which has no sensory input other than language to attempt to use those words in intelligible ways. We, of course, know what's happening under the hood. It's using linear algebra to replicate statistical patterns it observes in the languages that humans use. But it's unfair to judge that model based on its ability to generalize, conceptualize, maintain abstractions, because it hasn't had access to the multimodal input space that we humans take for granted when we're using language. We've been training since our emergence on this planet to infer the sensations, the experiences, the spatial relationships of objects that we're using words to describe, whereas a system which is training on language exclusively does not have the benefit of those additional input modalities.
Yeah, another thought that just kind of occurred to me and as we've been kind of fleshing this idea out is the fact that, like right now, what we're doing when we're having these language models learn our language is we're telling them, okay, understand the universe through the eyes of our collection of these discrete symbols, these words. So given our human vocabulary, understand the universe. And I feel like maybe we could unlock a lot more potential in some of these models if we 10x or 100x the actual number of terms that they have in their tokenized vocabulary, and allow them to compress things far better than any human can, and to convey things in a much more nuanced and, again, much more compressed manner than humans. Obviously, we want them to share the same vocabulary as humans as much as possible, but we potentially want to allow them, these neural networks, these language models, these autoregressive models, we potentially want to use them to find, for example, the words that we're missing in our language, the vector space that's critical to compression. Like, it's a compression search algorithm where you could maybe discover the most optimal words to introduce into the jargon of any specialized field of science, or some specialized, imagine some incredibly specialized field. Imagine a particle physicist, for example, and imagine the nuanced vocabulary that they have around these fundamental building blocks of atoms, and these quarks and leptons, and these fundamental particles, and how they interact, and what the color, for example, is. And all of these nuances. Like, when they say color, they're not referring to its refractive capacity to refract light. They're referring to something fundamentally different. And upspin. All these terms that share, they share a phenographic. They share a space with other terms, right? They're borrowed from more general terms in language, and they're given these very specialized symbolic meaning. But I just am intrigued by this idea that we can have language models, and just by scaling up the number of tokens that these language models are allowed to work with, we'll be able to really even innovate in the space of technical language through machine learning models that potentially could communicate with humans, and we as humans could develop more refined and more useful vocabularies in these technical areas. That's just a fun space to explore.
This feels like a wicked different actual user interface problem. If you thought deciding where to arrange buttons in two-dimensional interfaces was complicated, try coining new words and actually convincing humans to adopt them.
Well, I think it fundamentally becomes a problem of like which ideas could be compressed if we had those unique symbols, and like, yeah, I think it's a fun problem to, yeah, it's just fun. I'm enjoying this thought process of thinking about what that would look like in terms of GPT-3, to imagine maybe giving it far more, a far bigger dictionary of tokens. And yeah.
Speaking of fun, let's talk about human emotions. Clearly, they have adaptive utility because they're still around. And I think we can make some highly educated guesses about what that adaptive utility may be. I get really interested in the question when we look at current cutting-edge machine learning systems which do not incorporate conceptual emotions. And when I begin to wonder what they might stand to benefit from doing so.
So I think emotions are fundamentally similar to the noise input of a GAN in that they change the output, and they shift the distribution, and yet, you can also discover latent variables in that noise, which is what a lot of the fun GAN tools for generating faces are doing, right? And in fact, they actually discover latent variables for emotions in the GANs, for example, that generate faces. And so I look at emotions as basically what is the noise that's constantly being fed, and some of that. So we have this autoregressive model in our head, and emotions are kind of like the backdrop that kind of give us the unique set of heuristics with which to reason in that moment in time, which is why certain emotional states are more conducive to rationality than others, because certain ones give us a larger ensemble of underparameterized generalized heuristics with which to play, and others give us a much narrower set of heuristics with which to play in our thought process.
I like the idea of emotions as what one might liken to a temperature slider while playing with a language model, but I feel like there's more to it as well. It's not just the ability to increase divergence of a system's outputs. It's also it's also an opportunity for a net, in the sense that our brains are those nets, to steer outputs towards different categories of responses given different categories of inputs. When we think about the classic emotions, whether they're anger verging into rage, or whether they're happiness, sadness, love, fear, insecurities, which so many human emotions boil down to fear, since it's such a closely correlated with our core survival imperatives. It's fascinating to me when I think perhaps about a net that had a vector representation of every node, in which the different scalar elements of those vectors corresponded to different weights contingent upon the emotional state of that network. And perhaps if there was a way to train a network to adapt as humans do for contextually appropriate categories of responses given particular situations they might encounter.
Yeah, I think that what you're describing there is basically the process of discovering the latent variables that match the human set of emotions, which I think is a really fun thing that we should be discovering those latent variables in, for example, our GPT-3 models, so that we can, tweak them and play with them like we do temperature. So I completely agree that those latent models can be discovered that exactly match the set of human emotions that we are familiar with. However, the human emotions were selected for through a selection pressure that's completely different than the loss function of a neural network, right? Where you have an individual sense of identity and basically selfishness encoded into the genes, right? You have these selfish genes. And so that creates a whole different set of emotions when you have agents that are selected based on pressures that create this kind of a dance between selfishness and altruism that's effective for the species, compared to a neural network which has no notion of a loss function related to its own identity. And I think this gets into the fact that engineering the loss functions is really at the heart of the value alignment. I mean, that's really what makes a neural network intelligent, is its loss function more than its training data. I mean, both, but the loss function. And right now our loss functions are so simple. They're really just measuring the error in prediction, and they're not introducing some of the things that have been instrumental in evolution. And
it feels like
examples,
increasing the quality of input training data for a net is a very, perhaps one might say, naive, general, quick win optimization, whereas increasing the sophistication of the loss function itself has the potential to generalize that much more powerfully, to discover completely new things and
yes,
potentially facilitate the emergence of higher levels of intelligence in the system.
Absolutely. Yeah, and going back to what we were talking about earlier, I feel like one of the fundamental innovations to the loss function needs to be some measurements of modularity and parsimony. So some measurements of, for example, how compressed, how simple, how few parameters were you able to use to create this prediction, right? And that's where we are introducing Solomonoff induction. That's where we're introducing Occam's razor, combined with Bayesian reasoning, combined with statistics and probability, but introducing this idea that it's not just the most accurate model that we want, but the most efficient model that's able to, and the beauty about this natural world is that it appears to actually be very compressible, right? That there actually is a lot of order in this world, right? So the fact that we don't live in a universe of pure entropy, but that there are these negentropic systems of which we are, the most advanced that we are aware of, right, currently. But there are these negentropic systems, some of which are conscious, some of which are just simple, rules of molecules that create order. Just the fact that anything is intelligible at all about this universe says that there's quite a lot of order in this universe. And, that's the only thing that our models will actually be able to understand and compress, is that which is orderly. And, the entropy, of course, is non-compressible. Entropy is actually defined as that which is not compressible to anything of a shorter length. So,
there's a really beautiful, virtuous feedback loop. I envision it spiraling upward, where a net can use statistical tools to make heuristic inferences. And this could be a human mind, a language model, or something else entirely, and can ultimately recognize patterns so powerfully through those inferences that it could generalize into algebraic representations, essentially the discovery of the laws governing the behavior of the system that net is observing, which could ultimately spiral upward into rationality, the ability to describe those laws in a compressed, deterministic, explainable, intelligible sort of way, and to then build on those laws to observe much more subtle statistical aspects of the systems those nets are engaging with, and continue that feed forward process into higher levels of exploration and discovery.
Yeah. And I think that's fundamentally why Max's research is so interesting, and probably one of the most interesting applications of machine learning right now is to find, to innovate in physics, right? To basically create something that is able to find the fundamental mathematical rules of the universe that haven't been discovered yet, because there's doubtless many fundamental equations that are simple and beautiful, and I think beauty in many ways is an aesthetic judgment of how compressed something is, how orderly it is. It's a measure of simplicity, and so in a sense the beauty is our mind's value network approximating the parsimony of a model. And we find things that are symmetrical beautiful because that's a parsimonious. I mean, we only have to understand half of it. We understand the other half of it, right? That's an energy advantage in the prediction power of our understanding our mental model, right? So we
this
find
is
things.
Such an interesting thought. I've always conceptualized beauty as my own definition aligning more closely with something which is ready to survive. I might look at the curved lines of a sports car as something that's clearly designed to go fast, or the symmetrical features of a human face as something which clearly did a successful job replicating its DNA without introducing off-axis reproduction errors or something along those lines. But it strikes me that compressibility and elegance are themselves attributes of a system which is more likely to survive.
Yeah, this is a fun thought to explore. Is does the compressibility or the parsimony of a mental model have something to do with its aesthetic, attributes? I think a really interesting example of this is how polarizing the design of the Cybertruck is, and the fact that it's a low poly design compared to, you just mentioned curves. It's a low poly design compared to all the curves, and I find that to be very aesthetically pleasing. And some people don't, but it's a much more compressible model because it's low poly, and I think that there's been some interesting design trends away from all of the to a more flat and minimalist. I think that is why, for example, the minimalist design aesthetic is if there's one rule of good design, if you want a great aesthetically pleasing app, the one rule is simplicity, minimalism. Don't make the user think, right? Just that is the fundamental law of good design in products, and we know that every UI designer knows that the number one rule is avoid complexity, have something minimal and beautiful and elegant, right? I think
There's a way to have something so minimal, beautiful, and elegant that it actually encourages the user to think, which would be nice, but I'm still working on that one. Okay, but since you mentioned the Cybertruck, I personally find different eras of architectural aesthetics to be quite interesting, quite beautiful, and quite illuminative of the human condition as well. The example that comes to mind would be Soviet-era brutalist architecture. This idea of massive structures reaching into the sky, very simple geometric forms, with the stated intention of making humans feel insignificant compared to the edifices of the society they were building. And how, again, that can be a spiral moving in any number of different directions, where the environments we create, both in our individual micro-scale lives and in our collective macro-scale societies, ultimately determine the trajectory of our continued evolution as organic beings in a rapidly changing world that we're increasingly directing the trajectory of.
Yeah. Yeah. Fun stuff. I mean,
So fun.
it's really interesting just to try to spend a lot of divergent thought processes examining the parallels and the intersections between the ways that our mind work compared to the ways that a deep learning algorithm works. And I see, the more I study it, the more similarities and overlaps I see, and that makes sense because we are fundamentally, neural networks that are self-aware, and and so it's, I guess, still an open question if there's anything other than that. I mean, I don't know that we've ever been able to rule it out, except that that's all we find when we look at the brain is we just find this neural net architecture. And so, I guess the proof of the hypothesis is that we're now starting to see basically neural networks that confabulate. And I'm not sure that our autoregressive mental models of language are anything other than confabulation guided by some kind of discriminator. And I think that if you added a discriminator to something like GPT-3, you might get something much more similar to, the way the mind works. And so, I mean, confabulation makes perfect sense if you can imagine, for example, a mind given an input context sequence of symbols and just not given that discriminator. And I've seen confabulation so often in listening to example for children. My children often confabulate, and it's funny sometimes, but it's interesting to just see that dynamic.
I've found myself increasing in appreciation for intuition, emotion, and rationality as I've explored these concepts further. It's not that investigation into more technical fields leaves us in a more dry, barren, sterile world. For me, I found it to be just the opposite, where my ability to understand magnifies my ability to appreciate the aesthetics, the beauty, and the underlying harmony at every layer of the structures we observe in the natural world.
Absolutely. And that was probably my favorite idea that Max articulated well in that podcast that we both recently watched with him and Lex, was just the way that he expressed that there is nothing antithetical between a nuanced view of reality and the enjoyment of that reality and the gratefulness and the emotional satisfaction that we obtain from being conscious in this corner of the universe. In fact, the nuanced understanding of the fundamental mathematical substrates behind our conscious experience just is more color in our qualia, right? Just more color in our qualia, and that the way he articulated that was just really incredible, and I definitely concur and agree with his thoughts on that.
Agreed. For all the listeners, I'll be dropping a link to that episode in the show notes. Highly recommended. Well,
Absolutely.
we've just
One
explored
of the best.
We've just explored a number of some really interesting topics here. And there's so many more we could dive into, but I feel like that would probably be another hour, which would be more ideally organized into another episode for all of you listeners. Is there anything else you want to add for this one particularly, Zach?
No, not nothing that comes to mind. So it's been a fun conversation. Looking forward to many more.
Absolutely. Thanks everyone for joining us, and be sure to like, follow, and subscribe wherever you get your pods.